Welcome! In this session, we'll solve the problem sliding window maximum. This is a classic algorithm challenge that requires efficient solutions for handling sliding windows over arrays. Let's dive in and explore the problem along with various approaches to solve it. The problem is called sliding window maximum, and here's what it asks us to solve. You are given an integer array called nums and a number k, which represents the size of a sliding window. The goal is to figure out the maximum value in each sliding window as it moves one position at a time from the start of the array to the end. Once the sliding window has covered the entire array, you need to return a new array containing the maximum values from each window. Now, the input format specifies that nums is a list of integers, and its length can go up to 100,000. Each integer in the array falls between -10,000 and 10,000. The window size k is guaranteed to be at least 1 and no larger than the length of the array. Finally, the output format is a list of integers, with each number representing the maximum value found in a particular sliding window. Let's look at an example to better understand this problem. Here's the first example. Given nums equals 1, 3, -1, -3, 5, 3, 6, 7, and k equals 3, the output is 3, 3, 5, 5, 6, 7. To see why, let's break it down. The first sliding window covers the elements 1, 3, -1, and the maximum value is 3. The window then shifts one position to 3, -1, -3, where the maximum remains 3. The next window, -1, -3, 5, has a maximum of 5, and -3, 5, 3, also gives a maximum of 5. The following windows, 5, 3, 6, and 3, 6, 7, produce maximum values of 6 and 7, respectively. By collecting these maximum values, we arrive at the output array 3, 3, 5, 5, 6, 7. Let's look at another example. Here, nums contains just one element, 1, and k equals 1. The output is 1. Since the window size matches the array length, the only window we have is 1, and its maximum is simply the single element 1. So the result is 1. This example highlights how the problem handles the smallest input sizes. In the third example, nums is 9, 11, and k equals 2. The output is 11. With a window size of 2, there's only one window to consider, which is 9, 11. The maximum value in this window is 11. Thus, the output consists of a single element, 11. This example also demonstrates how the sliding window operates when the window size equals the array length. Now, let's go over some constraints and edge cases. The constraints of the problem ensure that the solution must be efficient. For example, the length of nums can go up to 100,000, meaning a naive approach that scans each window independently would be too slow. Instead, you need an O(n) solution. Edge cases to consider include situations like having just one element in nums, where the output is simply the array itself. If the window size equals the array length, the output is a single value, the maximum of the entire array. Be mindful of arrays with negative numbers or arrays where all elements are identical. Lastly, for large inputs, efficiency is critical. A helpful hint is to use a deque, or double-ended queue, to maintain indices of useful elements within the current window. This data structure enables you to efficiently find the maximum value as the window slides, meeting the problem's constraints. To solve the sliding window maximum problem, the brute force approach is the most straightforward way to start. Here, the idea is to iterate through every possible sliding window of size k in the array and compute the maximum value for each window. Specifically, for each starting index I in the array, we calculate the maximum of the next k elements, which gives us the result for that window. While this method is easy to understand and implement, it involves a nested loop structure, one loop to move the window across the array and another to find the maximum within each window. This results in a time complexity of O(n*k), which can become inefficient for large arrays or sliding windows. On the positive side, it uses no additional memory beyond a few variables, so the space complexity is O(1). However, the significant trade-off is performance, as the repeated computation of maximum values makes this approach impractical for larger inputs. To improve efficiency, we turn to an optimized approach using a deque, which is a double-ended queue. The key idea is to maintain the indices of elements in the current sliding window in such a way that we can quickly determine the maximum. The deque is structured to ensure that the indices within it are in decreasing order of their corresponding values in the array, from front to back. This makes the maximum value of the current window always accessible at the front of the deque. As we slide the window, we remove indices from the front if they are no longer part of the current window, and from the back if the corresponding values are smaller than the current element, as those smaller values are no longer candidates for the maximum. By efficiently managing the deque in this way, we avoid redundant comparisons and achieve a linear time complexity of O(n), since each index is added and removed from the deque at most once. The space complexity is O(k), which is the maximum size of the deque, as it only stores indices within the current window. Although the implementation is slightly more complex than the brute force method, it provides a significant performance boost, making it a highly efficient solution. An alternative approach involves using a max heap or a balanced binary search tree to maintain the elements in the current sliding window. In this method, we insert the elements of the current window into the data structure and extract the maximum value for each window. As the window slides, we remove the element that falls out of the window and insert the new element that enters it. While this approach is more efficient than the brute force method, with a time complexity of O(n)log k, due to the logarithmic cost of inserting and removing elements, it is still slower than the deque approach. The space complexity remains O(k), since the heap or tree only needs to store the elements in the current window. However, the overhead of maintaining the heap or tree structure, combined with the increased implementation complexity, makes this method less appealing compared to the deque-based solution for this particular problem. Based on the analysis of different strategies, we select the optimized approach using a deque as the most suitable solution for this problem. Its linear time complexity allows it to handle large input sizes efficiently, and the constant time operations for insertion and removal make it highly performant. Unlike the brute force method, which suffers from redundant computations, the deque approach avoids unnecessary work by discarding smaller elements that are no longer relevant to the current window. Additionally, while the heap-based method is a viable alternative, its logarithmic overhead makes it less competitive in this scenario. The key insights driving the deque approach are that we only need the maximum value in the current window, and we can efficiently track this by maintaining indices in a structured way. By leveraging these observations, the deque-based strategy strikes the perfect balance between performance and complexity, making it the optimal choice for solving the sliding window maximum problem. The problem we're solving is to find the maximum value in each sliding window of size k as it moves across the array nums. This means we need to compute the maximum for every possible subarray of length k as the window shifts from the beginning to the end of the array. While this might seem straightforward at first glance, doing this efficiently is the real challenge. One simple approach to solve this problem is the brute force method. Here, we start by initializing two important variables, n, which represents the length of the array nums, and an empty list called result to store the maximum values for each window. Once these are set up, we iterate through the array, ensuring we only consider valid windows of size k. This is achieved by looping from index 0 to nk, where nk represents the last position where a full window of size k can fit. Each iteration will focus on a specific sliding window, and will calculate the maximum value for that window in the upcoming steps. Now, for each index I in our loop, we extract the current sliding window by slicing the array nums from index I to I plus k. This gives us the subarray containing exactly k elements for that window. Next, we calculate the maximum value within this window. Python provides a built-in function, max, which allows us to find the largest number in the subarray with a single function call. Once we have the maximum, we add it to our result list. This process is repeated for all valid sliding windows, ensuring that every window's maximum is captured. Finally, after iterating through all possible windows, we return the result list. This list will contain the maximum values for each sliding window, providing the solution to our problem. While this approach is simple and easy to understand, it has performance drawbacks that we'll explore further. The brute force approach has a clear limitation when it comes to efficiency. To understand why, let's analyze its time complexity. For each sliding window, we compute the maximum by iterating over all k elements, which takes k time. Since there are nk plus 1 windows in total, the overall time complexity becomes O, nk plus 1, asterisk k. For large arrays, this simplifies to approximately O, n asterisk k, which can be prohibitively slow if both n and k are large. The space complexity, on the other hand, is more favorable. We only use O1 additional space, excluding the output list, as we're not relying on any extra data structures. However, the inefficiency of this algorithm becomes apparent when n and k are close in size. For instance, if k is half of n, the number of calculations grows significantly. We should also consider edge cases. If k is 1, we don't need to do any real calculations since each element is its own maximum. If k equals n, there's only one window, and its maximum is the largest value in the entire array. Finally, if the input array nums is empty, the result should also be an empty list. To implement the brute force approach, we primarily rely on lists. The result list is crucial as it stores the maximum values for each window, and Python lists are ideal for this task due to their dynamic nature and constant time appending. The sliding window itself is just a conceptual tool here, as we extract subarrays directly from the input array without maintaining a separate data structure for the window. While the brute force method works, there are optimizations that can drastically improve performance. One such optimization involves using a double-ended queue, or DEQ. A DEQ allows us to efficiently track potential maximums as the window slides, eliminating the need to recompute the maximum for each window. This reduces the time complexity to O, n. Another advanced optimization involves pre-processing the array for range queries using techniques like sparse tables or segment trees. These methods allow for constant time range maximum queries after an initial pre-processing step, though they come with additional space and setup time costs. These optimizations make the algorithm significantly more scalable for larger inputs. Here, we start by importing the DEQ class from the collections module, which will help us efficiently manage the sliding window. Inside the solution class, we define the max sliding window method, which takes two parameters, nums, the list of integers, and k, the size of the sliding window. As a first step, we handle edge cases. If the input list is empty or the window size is 0, we return an empty list. Next, we initialize a few variables. N stores the length of the input list, result will hold our final output, and DQ is our DEQ, which will help us track indices of elements in the current window. Now we enter the main loop, iterating over each index in the nums array. The first task inside the loop is to ensure that the DEQ only contains elements within the current sliding window. If the front of the DEQ points to an index outside the window's range, we remove it using popleft. Then, we remove indices from the back of the DEQ while the corresponding elements in nums are smaller than the current element, ensuring the DEQ always maintains indices in decreasing order of their values. Once the DEQ is updated, we append the current index to it. If the current index is at least k1, meaning we've processed enough elements to form a complete window, we append the maximum value of this window to the result by accessing nums at the index stored at the front of the DEQ. Finally, after completing the iteration over the input list, we return the result array. This array contains the maximum values for each sliding window of size k. By using a DEQ, we maintain an efficient O, n, time complexity, since each element is added to and removed from the DEQ at most once during the entire process. This makes the solution highly efficient, even for large input arrays. With that, our implementation is complete. Here, we begin the Java implementation of the sliding window maximum problem. First, we import the necessary utility classes. The max sliding window method is defined to take an integer array nums, which represents the input list, and an integer k, which represents the window size. We start by handling some edge cases. If the input array is null, empty, or if the window size is 0, we return an empty array since there are no valid windows to process. Next, we initialize variables. N holds the length of the input array, and result is an array to store the maximum values for each sliding window. We also initialize a DEQ to efficiently manage indices of the elements within the window. The loop iterates over the array, and the first operation inside it checks if the leftmost index in the DEQ is outside the bounds of the current window. If it is, we remove it from the front of the DEQ. This ensures that the DEQ only contains indices within the current sliding window. Then, we remove indices from the back of the DEQ if their corresponding values in the array are smaller than the current element. This step ensures that the largest value in the window is always represented by the index at the front of the deque. After maintaining the deque structure, we add the current index to the deque. This is followed by a crucial step. Once the window has reached its full size, meaning I is greater than or equal to K1, we record the maximum value of the current window into the result array. The maximum value is always represented by the element at the index stored at the front of the deque. Finally, after processing all elements, we return the result array, which contains the maximum values for each sliding window. This implementation is efficient, operating in O(n) time, as each element is added to and removed from the deque at most once. In this example, we are given an array nums with values 1, 3-1, 3, 5, 3, 6, 7, and a window size k of 3. Our goal is to find the maximum value in each sliding window as it moves across the array. To begin, we initialize 3 components: an empty result list to store the maximum values, a deque to manage the indices of elements in the current window, and the given array and window size. In the first iteration, where I equals 0, the current number is 1. We add the index 0 to the deque, which now holds 0. Since the window size is still smaller than k, no maximum is calculated yet. In the second iteration, I equals 1, the current number is 3. Before adding this index to the deque, we remove smaller elements from the back of the deque. Since 1 is less than 3, the deque becomes empty. We then add index 1 to the deque, which now holds 1. Again, since the window size is still smaller than k, no maximum is calculated. On the third iteration, I equals 2, the current number is -1. This time, no elements are removed from the deque since -1 is not greater than the current maximum in the deque. We add index 2 to the deque, which now holds 1, 2. Now that the window size equals k, we calculate the maximum for this window, which is nums 1 or 3. The result list is updated to 3. For the fourth iteration, I equals 3, the current number is -3. We check for indices that are out of the window, but none need to be removed. We then add index 3 to the deque, which now holds 1, 2, 3. The maximum for this window is still nums 1 or 3, so the result list becomes 3, 3. In the fifth iteration, I equals 4, the current number is 5. First, we remove indices that are out of the current window. Index 1 is removed since it falls outside the range of the current window. Next, we remove smaller elements from the back of the deque, which includes indices 2 and 3, as both -1 and -3 are less than 5. We then add index 4 to the deque, which now holds 4. The maximum of the current window is nums 4 or 5, so the result is updated to 3, 3, 5. This process continues for I equals 5, I equals 6, and I equals 7, with similar steps of removing out of window indices, maintaining descending order in the deque, and calculating the maximum for each window. By the end of the array, the final result is 3, 3, 5, 5, 6, 7. In the next example, we work with the array nums equals 9, 11, 8, 5, 7, 10, and a window size k of 2. We start by initializing the result list as empty and the deque as empty. In the first iteration, I equals 0, the current number is 9. We add index 0 to the deque, which now holds 0. In the second iteration, I equals 1, the current number is 11. Before adding this index, we remove smaller elements from the back of the deque. Since 9 is less than 11, we remove index 0. The deque is now empty, and we add index 1, so the deque holds 1. The maximum for this window is nums 1 or 11, and the result list is updated to 11. For the third iteration, I equals 2, the current number is 8. Since 8 is less than the maximum value currently stored in the deque, we simply add index 2 to the deque, which now holds 1, 2. The maximum for this window is still nums 1 or 11, so the result list becomes 11, 11. This process continues for the remaining iterations, following the same steps of adding indices, removing out of window elements, and maintaining descending order in the deque. By the end of the array, the final result is 11, 11, 8, 7, 10. In this final example, we are given the array nums equals 4, 3, 2, and a window size k of 1. Since the window size is 1, each element forms its own window, and the maximum for each window is simply the element itself. We initialize the result list as empty and the deque as empty. For each index I, we add the current index to the deque and directly record nums, deque, 0, as the maximum, since the deque always holds at most one index. The result list is updated sequentially as 4, then 4, 3, and finally 4, 3, 2. The final result is 4, 3, 2. The time complexity of our optimized solution is O, n, where n is the length of the input array nums. Let's break this down step by step. First, the algorithm iterates over the array using a single for loop. This traversal alone contributes O, n, since we visit each element exactly once. Next, the core of our solution involves operations on the deque. Each deque operation, like appending, popping, or removing elements from the front or back, is O1. Now, let's look more closely at these operations. When removing indices that fall out of the current window, the condition only triggers at most once per element, and the actual removal takes constant time. Similarly, when removing smaller elements at the back of the deque, each index is processed at most once during the loop, which means this logic also contributes O1 per element. Finally, appending the current index to the deque is another O1 operation. Since all these deque operations are tied directly to the number of elements in the array, their combined time is linear, or O(n). Now, let's consider the overall contribution of these operations. Since each element is added to and removed from the deque exactly once during the algorithm's execution, the total cost of all deque operations remains O(n). Additionally, for each sliding window starting from index k1, we append the result of the maximum value from the deque into the result list. This append operation, which happens once per window, contributes O(n) in total as it is performed approximately n(k plus 1) times. When we combine the costs of traversing the array, performing deque operations, and appending results, the overall time complexity of the algorithm remains linear, or O(n). This efficiency is a result of minimizing redundant computations and ensuring each operation is constant time within the loop. Let's now focus on the space complexity of the solution, which is OK, where k is the size of the sliding window. This comes primarily from the space used by the deque. The deque is used to store the indices of elements within the current window, and its size is directly proportional to the window size k. At most, the deque will contain k indices at any given time, so the space required for the deque is OK. Additionally, we have the result list, which stores the maximum value for each sliding window. In the worst case, there will be approximately n(k plus 1) sliding windows, meaning the result list will require O(n) space. However, since the deque space usage of OK is typically the dominant term when k is much smaller than n, the overall space complexity of the algorithm is OK. This space efficiency is another advantage of using the deque-based approach. To better understand the efficiency of this solution, let's compare it with the brute force approach. The brute force method involves iterating over all possible sliding windows of size k and calculating the maximum for each window. This requires a nested loop structure, where the outer loop runs O(n) times to determine the starting index of each window, and the inner loop runs O(k) times to find the maximum value within each window. This results in an overall time complexity of O(n*k). In contrast, the deque-based solution eliminates the need to repeatedly compute the maximum for overlapping elements within the same window. By maintaining a deque of indices that represent potential maximums, we avoid redundant comparisons and reduce the time complexity to O(n). This makes the optimized approach significantly more efficient, especially for larger arrays and window sizes. Finally, let's analyze the best, average, and worst-case scenarios for the optimized solution. In the best case, where all elements in the array are equal, the deque operations still occur for each element, and the time complexity remains O(n). In the average case, for a randomly distributed array, the deque operations scale linearly with the size of the array, which also results in O(n) time complexity. In the worst case, where the array is strictly increasing or strictly decreasing, each element is added and removed from the deque exactly once, still maintaining O(n) complexity. To mathematically prove this, we observe that for n elements, each is processed exactly once during the array traversal and added or removed from the deque at most once. This means the total number of deque operations is proportional to n combined with the linear array traversal, the overall time complexity is O, n. The space complexity, dominated by the deque storage proportional to the window size k, is O, k, ensuring that the solution remains efficient in both time and space. When solving the sliding window maximum problem, there are several common mistakes to watch out for. One of the most frequent errors is using a nested loop to calculate the maximum for each window. While this approach might seem straightforward, it results in a time complexity of O, n squared, which becomes highly inefficient for large arrays and can lead to time limit exceeded errors. The reason this is problematic is that it doesn't take advantage of the overlapping nature of the sliding windows, leading to redundant computations. Another mistake is neglecting to handle edge cases. Scenarios such as an empty array, a window size of 1, or a window size larger than the array itself can cause runtime errors or incorrect outputs if not explicitly addressed. Additionally, errors in managing the deque, such as failing to remove indices that are no longer within the current window or not maintaining the correct order of elements, can result in incorrect maximum values. Finally, overcomplicating the logic by combining multiple steps, like deque cleanup and adding new elements, may make the code harder to debug and reduce its clarity, which can lead to logical bugs during implementation. Another common issue is misunderstanding the space complexity of the deque approach. Some mistakenly believe that sliding operations result in O, n squared, space complexity, but this is incorrect. The deque only stores indices relevant to the current window, so its space usage is proportional to the window size, making it O, k. Now, from an interview perspective, this problem is a great test of your ability to optimize brute force solutions using the sliding window technique. Specifically, interviewers are looking for your ability to combine this pattern with a deque or monotonic queue to efficiently calculate the maximums. Make sure you're comfortable with deque operations like append and popleft, as well as their O(1) time complexity. Additionally, discussing edge cases during interviews demonstrates thoroughness, which interviewers value highly. Lastly, be prepared to explain the trade-offs between the brute force approach, which is simpler but slower, and the deque-based approach, which is more efficient with O(n) time complexity but requires careful management of both time and space efficiency. This sliding window problem is closely related to several others, each of which builds on similar concepts. For instance, problem 239, sliding window maximum, is the direct problem we're addressing here. Problem 1425, constrained subsequence sum, also leverages a deque to maintain a sliding window of maximum values. Similarly, problem 862, shortest subarray with sum at least k, involves efficiently managing sliding windows, while problem 480, sliding window median, introduces the challenge of maintaining sorted data within a sliding window. In terms of alternative approaches, the brute force method involves iterating through all subarrays of size k and finding the maximum for each. While this method has a time complexity of O(n squared and requires minimal space, it's computationally expensive and not suitable for large arrays. On the other hand, the optimized deque approach stores indices of maximum candidates, removing irrelevant indices as the window slides. This method achieves O(n) time complexity and O(k) space complexity, making it efficient but requiring careful handling of the deque. Another optimized approach is to use a max heap to track the elements within the current window. This method offers a time complexity of O(n log k) and a space complexity of O(k). While it's easier to implement compared to the deque method, it's slower due to the logarithmic overhead of heap operations. Finally, there's the dynamic programming approach using a sparse table, which pre-computes the maximums for all ranges of size k. This approach is very fast for static queries, with a time complexity of O(n) and space complexity of O(n). However, it introduces some overhead during the pre-computation phase, which may not make it suitable for all use cases. Each approach has its trade-offs, and the best choice depends on the specific constraints and requirements of the problem at hand. Great job! To wrap up, we solved the sliding window maximum problem and highlighted the importance of using efficient data structures like the deque. Remember to practice similar problems to solidify your understanding. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!